Hello students, in this video we'll solve a classical problem about writing the natural numbers as a finite number of arithmetic progressions. Let's define the relevant terms. Recall, a sequence is an arithmetic progression if it has the form, has to look like this. Has to look like a, then a plus d, then a plus 2d, a plus 3d, and it's a sequence, so it goes on forever, right? Okay. Now note that if, for example, a was equal to 1, so here a and d are in n, right? And so, of course, a trivial case of this would be a equals d equals 1, and then I have 1, 2, 3, I just get n, right? Is the natural numbers, right? So when a and d are equal to 1, I get the natural numbers. Okay? I claim that's in some sense the only case. In other words, the proposition is the following. We cannot write the natural numbers n as the union of finitely many arithmetic progressions with different common differences. Okay, now why did they have to be distinct over here? Well, let's think about the situation when I can do what? I could take, for example, a equals 2 and d equals 2, right? So if I did a equals 2, just note again, so note, if a equals 2 and d equals 2, then what do we get? We get 2, 4, 6, then that corresponds to the evens, right? If I took a equals 1 and d equals 2, then what do I get? Then I get the what? Then I get the odds, right? So in particular, if the common difference is allowed to be the same and not distinct, then I can unite the evens united with the odds will give me what? Will give me all of n, right? So in other words, if they are not distinct, then this statement is not true. But if they're distinct common differences, then I cannot write n. And let's see how that's the case. So here's the proof. And remarkably, it uses complex analysis. So proof, as we've seen, there's a lot of number theory that's embedded into complex analysis, which is beautiful. It's just one of the many connections that mathematics has between different fields. You wouldn't expect complex analysis to play a role in this, but it does. Okay? Proof. Suppose that n could be written as the union of S1, union S2, union all the way down to S, let's say D. I shouldn't use D over here, so let's use something else. Let's use SK, where SI is equal to AI plus LDI, L bigger than or equal to 0, right? So SI has common difference what? So in other words, SI and these, of course, these L are really what? Really an N or 0, right? N or 0. Okay, excellent. And then that's what we've done, okay? Excellent. And so now what I'm going to do is the following. So now I'm going to use these indices. I'm going to consider the following function. Consider the function f of z is the sum, n goes from 1 to infinity of z to the n, okay? I've summed over all the natural numbers here, and this function f of z is equal to what? This function f of z is equal to z over 1 minus z. Perfect, right? And this is valid for all z less than 1. And there's, of course, this defines a holomorphic function everywhere except for the point z equals 1, right? And there's, of course, a pole at z equals 1 as a pole only at z equals 1. So this is a meromorphic function. So f is meromorphic. F is meromorphic with a pole at 1. Okay, but now what can I do? I know that n is the union of all these arithmetic progressions, right? So I also know, so f of z therefore can be written as what? Is the sum, L goes from 1 to infinity, right? Of z to the a1, for example, it's going to be a1 plus, L goes from 0 to infinity, plus L d1, right? That gives me all the terms in these first one, S1, plus the sum, L goes from 0 to infinity, of z a2 plus L d2, plus all the way down to what? Plus all the way down to the sum, L goes from 0 to infinity, of z to the a what? Z to the ak, and then dk, right? Plus L dk. Good. Excellent. I know what these things converge to. This thing over here converges to what? This converges to z to the a1 over 1 minus z to the d1. This thing over here converges to z to the a2 over 1 minus z to the what? To the d2. All the way down to what? Z to the ak over 1 minus z to the dk. All right, excellent. Now what am I going to do? So now, without loss of generality, assume that d1 is bigger than all the dj, right? dj for all j. They're distinct, right? From 2 to k. So d1 is the largest of these exponents over here, right? So let's call this of course will be like the right-hand side of my equation for f. And then this over here would be the left-hand side of the equation for f, right? So what happens to the left-hand side? So the limit as z approaches e to the 2 pi I over d1 of the left-hand side is a finite number. But if I do the limit as z approaches e to the 2 pi I over d1 of the right-hand side, what's going to happen over here? All of these terms over here are perfectly fine, right? There's going to be no singularities over here because d1's larger than all those dk, right? Which means that I'm not going to get to, because e to the 2 pi I over d1, so like dk over d1 is what? dk over d1 is going to be less than 1, so I can't get to 2 pi I, so it's not going to hit 1. It's not going to hit 1 at all, so these things are fine. What's the issue over here with this term over here? As z approaches e to the 2 pi I over d1, this approaches 1 minus e to the 2 pi I. E to the 2 pi I is equal to 1, therefore the left-hand side is what? Is infinite. So if I can partition n into a finite number of arithmetic progressions with a distinct common differences, then I can write this function f of z in two ways. On one side of the equation, it's bounded as I approach e to the 2 pi I over d1. On the right-hand side of the equation, as I approach e to the 2 pi I over d1, I blow up, I go to infinity. That contradicts the fact that n can be written as a finite number of arithmetic progressions, right? That's remarkable, right? So in other words, seemingly there's this problem in number theory that has nothing to do with complex analysis, but I can extend the problem to a problem in complex analysis and use some properties of roots of unity, right? So the roots of unity make an appearance here. And they appear in a very specific way because what I've done is I've said, this is a meromorphic function over here, this f of z is a meromorphic function. But now what's happening is that if I can write it as a finite number of distinct common arithmetic progressions with distinct differences, then I'm getting a whole bunch more, and still meromorphic, I'm just getting a whole bunch more singularities over here, right? So in other words, this will induce more singularities if I could write n in this fashion. So complex analysis plays an important role in the study in some of these number theory problems, which we'll continue to see in further videos. Thank you very much.